Now, so that example showed you how you can compute the inverse of a given matrix, right? And that's an important operation. And in many scenarios, you will be needing to compute the inverse of a given matrix that is given to you. But let's see how that could be used in solving our original system equation, right? Because that's an important point, because we need to invert the matrix in order to find the solution of the system equation. Okay, so recall where we were there with respect to our original problem. We had x equal to m inverse v, where we need to take this matrix, take an inversion of that, and multiply that by the v vector. Now, in the previous slide, going through the multiple stages, which is determining the determinant, and then determining the adjoint of the matrix M, which involved 3 steps: minor matrix, cofactor matrix, and taking the transpose of the cofactor matrix allows us to compute the adjoint. Then we did what? We did use the equation 1 divided by determinant of A multiplied by adjoint of matrix itself. That gave us the matrix inversion, which we have computed. So in this case, we can write that, this is what we got after taking M inverse. We showed you how to compute this. Now I will take this matrix and multiply that by the V vector. Okay, and then this will result in a new vector, right? And that essentially is the solution of the X. So if I do carry out this matrix to vector product, I will essentially arrive at a vector which is defined here. Now we have 3 entries in this vector, and each are corresponding to the solution of the overall problem. Or another way to think about that, once we arrive here, the solution to the overall equation is x equal to minus 29 by 31. The solution of y is 177 by 31, and z is equal to 112 divided by 31. So these are the 3 values of x, y, and z that will essentially solve for the set of linear equation that we have, right? And that is the final solution from the set of equations that we can have. Okay, so summarizing, the matrix inversion involves basically numerically is implemented using this equation, and there are multiple steps. You first compute the determinant, then you compute the adjoint, which has 3 sub-steps. Now it turns out if the determinant is 0, the transformation is squashing the dimension into the smaller one, and there is no inverse, right? So in case if the determinant of the matrix come out to be 0, we cannot invert that matrix at all, and that operation is not feasible. So for this operations to be meaningful, or inversion of a matrix to exist, the determinant of the matrix has to be non-zero, and that's an important concept that we should remember. Okay, again, why? Because we cannot unquash a line into a plane, and that's why geometrically this is not feasible, and that's why the inversion is not meaningful if the determinant of that matrix is 0.